Hello, everyone, and welcome back. In the previous video, we introduced what's known as the trapezoidal rule that can be used to approximate the value of a definite integral. Now, today what we're going to introduce is what's called a Simpson's rule. And so if you go all the way back to the Riemann sum, think about what we did here. We approximated the area under a curve using rectangles. And in particular, the top of those rectangles you can think of as constant functions. And the reason I say this is because if you think about the trapezoidal rule, we don't have rectangles, we have angled tops to these things. And so you can think of this as using linear functions to approximate the top of these rectangles. If you look at the whole curve together, if you look at just these tops, you're taking something that was very, very curvy potentially, and making it straight. You're sort of using little straight lines to approximate it. Well, Simpson's method or Simpson's rule takes this even further. Simpson's rule says that instead of using linear functions, let's go one higher. Let's take quadratic functions. And what we're going to see is that using quadratic functions greatly improves the accuracy of our approximation of these integrals, even when you have relatively few steps. We saw with the trapezoidal rule that you need lots of steps in order to get a very, very small error. That's the benefit of Simpson's rule. It's slightly more complex, but the trade-off is that the error is much smaller when you have less steps. So let's jump into it. Okay. So let's for a moment imagine that, again, I have a curve. I will draw it as positive just for the sake of explanation, but of course, everything will work if you have a negative function as well. You just have this abstract notion of area again. So let's suppose I have a function that might look like this. So maybe something that looks a little bit cubic. And we want to find, so we want to approximate the integral from a to b of f of x dx. Okay, so the way that we're going to do this is we are going to find a parabola. So for each, we're going to break this up in the same way using x0, x1, x2, x3, and we're going to find parabolas that go through these points that are discretized along our curve, y1, y2, y3, y4. So we're going to start with the same procedure, but let me show you, for example, if this is one point, and let's say, well, I'll draw the parabola first. Let's approximate this region right here using these 3 points. So this is yi minus 1, yi, and yi plus 1. You could probably see why I'm hesitant to do this over the whole curve because it's going to be very, very messy. So I just want to draw one parabola in here so that you can get an idea of what we're doing to approximate. Now, the first thing that we're going to do is we're going to let delta x equal to b minus a over n again. And then we are going to let n be even. So we need an even number in order to apply Simpson's rule. And this comes from the fact that if you want to define a parabola, you need 3 points to define it. So you're going to see why this becomes necessary as we progress. But a parabola through the points, well, the first point is xi minus 1, yi minus 1, which is just f of xi minus 1, xi, yi, and xi plus 1, yi plus 1. Okay, so that's the green parabola curve that I have written right there. Okay, so let me do a little experiment here. Let me do some illustration, and it's just going to be with a little toy, and we'll see how this scales up. Okay, so maybe let's put a little divider here. Let's take, say, x0 is equal to minus h. Let's take x1 is equal to 0, and let's take x2 is equal to plus h. Okay, so these are my 3 x points, and we're going to say with h is equal to delta x, which is b minus a. So typically, as you progress through mathematics, people don't write delta x because it's 2 letters. We're lazy as mathematicians. We like to use h instead. So I'll just use this as the shorthand here. You can replace it with delta x if that makes you more comfortable. So our parabola, without finding the coefficients yet, is going to be ax squared plus bx plus c. Now, a, b, and c are going to be determined from those 3 points on my curve, but without that yet, let's see the area under the parabola. And so, I'm using this, in the abstract sense again. It doesn't necessarily have to be under if this thing was negative, but area under the parabola, AP, in my case, over this interval from x0 to x2. So we imagine we only use like 3 points to discretize this space. Well, then we've got this nice little integral of a parabola, a nice polynomial. We can deal with that. That's nice and easy for us. So we get ax cubed over 3 plus bx squared over 2 plus cx. And that's running from minus h to h. And in fact, if you plug h into this thing, you're going to get 2ah cubed divided by 3 plus 2ch. And sometimes what we'll do here is we'll take h over 3 out front, and we will go 2ah squared plus 6c. So the h over 3, this is just a custom that people use when they do Simpson's rule. But okay, that's just a straight integration. That's nothing too exciting yet. Let's figure out what a, b, and c are in this case. Okay, so since the parabola goes through the points, so parabola y is equal to ax squared plus bx plus c goes through. Now, it goes through the point minus h, that's x1, that's x0. It goes through the point minus h, y0, 0, y1, and h, y2. Okay, just for illustration. Well, then, going through the point minus h, y0 is the same as saying that y0 is equal to a h squared minus bh plus c. All I did was put x equal to h in there and set it equal to y0. Similarly, I have y1 is equal to c because x is equal to 0. And y2 is equal to ah squared plus bh plus c. Okay, so if we look at these, we call this one 1, we call this one 2, call this one 3. Well, right away, we see that c is equal to y1. And then if we add both equations, so if we take 1 plus 3, this gives me y0 plus y2 is equal to 2ah squared plus 2c. And from this equation, we can see, in fact, that 2ah squared is equal to y0 plus y2 minus 2y1. And you might be thinking to yourself, what was the point? Why did you leave that as 2ah squared? Well, remember, I'm doing this all in service of figuring out what this integral is equal to. And since I factored out the h over 3, I've got 2ah squared. So there's a little foresight in here. So now we've got everything that we need, right? We know what c is. We know what 2ah squared is. And so we can put this together, and this gives us AP is equal to h over 3 2a h squared plus 6c, which is equal to h over 3, h over 3, and then y0 plus y2 minus 2y1, and then plus 6y1, which is the same as saying, in this case, let's order them. So y0 plus 4y1, and then plus y2 here. Now, here's the thing. We can repeat this for any values in h. We can take that parabola. So what I did is I centered my parabola at 0. So the vertex is at 0. But if I move it left and right, nothing is going to change, right? The area underneath the curve is still going to be the same. I just recentered it at a different place. And that comes from the fact that the x's never show up in this equation. It's the values of y0, y1, and y2, which are determined by the original function. So that also tells me, similarly, the area, let's say under the parabola, through, let's say, generally any collection of points, xi minus 1, yi minus 1, xi, yi, and xi plus 1. So any triplet of points is given by the same formula. So AP is equal to h over 3, and then yi minus 1 plus 4yi plus yi plus 1. Every single one of these little parabola approximations that you make here is giving you this same value. And so what Simpson's rule tells us, or what it dictates, is that we can approximate the integral using these parabolas, and it gives us this approximation. The definite integral here is approximately h over 3 y0 plus 4y1 plus y2 plus, so that's under the first parabola. Then under the second parabola, you move forward. So you get y2 plus 4y3 plus y4. And then you continue this process. You're moving forward 2 at a time. So you're using the odd numbers in order to be in the middle of the parabola, and the even numbers in order to define the endpoints of your parabola. And so this goes all the way up until you get to the last parabola. Sorry, the 3s are looking bad today. And you get yn minus 2 plus 4yn minus 1 plus yn, which is f of b. But here's the thing. You can actually rearrange this in a really nice way. The same way that the trapezoidal rule had a little pattern to it, Simpson's rule has the same thing. y0 only shows up once. y1 similarly only shows up 4 times. But now y2 shows up in the first parabola in the sum, and it shows up in the second parabola in the sum as endpoints, either the right endpoint or the left endpoint. So this gives me 2 y2s. And then I've got 4 y3s again, since it's a midpoint of a parabola. And then I've got 2 y4s. It ends the second parabola and it starts the third parabola. And then you repeat this, you alternate between the 4s and the 2s until you get to the end here. You get 2yn minus 2 plus 4yn minus 1, and then plus yn because it only shows up once on the end. So this is known as Simpson's rule. Let me write it down properly so that everybody can see what is actually being done here. So Simpson's rule. So to approximate the definite integral a to b of f of x dx, we use, let's call it S for Simpson. We use delta x over 3. So that was my h. Remember, I just set h equal to delta x for a for a quick and easy way of writing it. And then f of a. So that's f of x0. Maybe I'll keep everything in terms of x's. x0 plus, and now we've got 4 f of x1 plus 2 f of x2 plus 4 f of x3. So all the odd numbered ones are going to get 4s. And then dot, 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 plus 2 f of xn minus 2 plus 4 f of xn minus 1 plus f of xn, which is f of b, the right endpoint, with x0 equal to a, x1 equal to a plus delta x, x2 equal to a plus 2 delta x, and so on and so forth until xn is equal to b, and n is even with delta x equal to b minus a over n. So there's a pattern to the coefficients here, right? 1 on x0, 4 on x1, 2 on x2, right? So the pattern goes 1, 4, 2, 4, 2, 4, 2, right? And you run that out, and then you do the final one. You go 2, 4, 1 for the endpoint. So it's much more complicated than the trapezoidal rule. The trapezoidal pattern was 1, 2, 2, 2, 2, 2, 2, 2, 2, 1. So this one has an alternating pattern that makes it slightly more complicated. So let's do what we did with the trapezoidal rule. Let's do an example. Let's see how we compare to the exact value. So example, use Simpson's rule to approximate let's do the integral from 0 to 2, 5x to the 4 dx with, let's say, n equal to 4. That's an even number. We can do that. And we want it to be small enough that we can do pencil and paper computations here. Okay, so f of x is equal to 5x to the 4. And x0 is equal to 0. Sorry, we should compute delta x first, pardon me. Delta x is equal to 2 minus 0 divided by 4, which is equal to 1/2. So we're taking steps of 0.5. And now I can get my x0, which is 0, 1/2, 1, 3/2, and finally 2. So that Simpson's rule tells me I get delta x over 3, and then let's start plugging in the values. So, sorry, f of x0 plus 4 f of x1 plus 2 f of x2 plus 4 f of x3. So the odd numbered ones get a 4 in front of them, plus f of x4. Let's start filling things in. So 1/2 divided by 3, that's 1/6. F of 0, f of x0, which is f of 0, is 0, plus 4, and then 1/2 to the 4, that's 16 times 5. We have 5 over 16, plus 2, and now 1 to the power of 4 is 1, so times 5 is 5, plus 4, and in this case, we get 3 over 2 to the power of 4, and then multiply that by 5. You might have to get your calculator out, but I can tell you that's 405 over 16. And then finally, you put 2 in there. You're going to do 2 to the power of 4, and then multiply by 5. You get a nice 80. Again, you might need a calculator, but it's okay. In this case, you get 32 and 1/12. So I'm going to write it as an improper fraction, just because I want you to see what, let's compare it with the exact answer. And you're going to see why I wrote it as 32 and 1/12, because I don't think I've ever used improper fractions or these sort of this notation before. I typically use improper fractions. But the exact value is, well, we can just compute this. We're good at these integrals now. This gives me x to the 5 from 0 to 2, which is 32 minus 0, which is equal to 32. So the error is equal to 1/12. That's why I put that out back like that, because we overestimated by 1/12 using Simpson's rule. Now 1/12 is a pretty small number, and the percent error, so if you take 1/12 and divide it by 32, this thing is like 0.3%. So 0.3%. So it's very, very, very small. And that was just with 4 subintervals, right? This is an extremely accurate computation. If you want to go back, use the trapezoidal rule and do the same thing with n equal to 4. You'll see that it doesn't perform quite as well here. And much like the trapezoidal rule, we have an error estimate. I can explicitly tell you how big the error can possibly be. So the error estimate for Simpson's rule well, in this case, we need the 4th derivative of the function that you're taking the integral of to be continuous. And just like trapezoidal rule, we need m to be an upper bound. It's any upper bound on the absolute value of the 4th derivative on the interval AB. Then the error ES, which is the difference between the actual integral minus the n-step Simpson's rule, with n even steps, so it has to be an even number to do this, satisfies the inequality. You have the Simpson's error is less than or equal to, there's the m, just like the trapezoidal, b minus a to the power of 5 divided by 180 n to the 4. Now remember, with the trapezoidal rule, we had over n to the 2. So this thing, using the order notation, is like n to the minus 4. So if your function is fixed, if your interval is fixed, this tells you Simpson's rule is going to outperform, or it should be expected to outperform the trapezoidal rule. And that comes from the fact that the error is getting small fast. It's getting small like 1 over x to the 4, right? That gets smaller faster than 1 over x squared. So this is really interesting, right? This is how a lot of numerical integration actually works. Like if you type in, what is the integral from 0 to 2 of 5x to the 4, you will probably get a Simpson's rule approximation of this thing. And again, this is a really easy thing to program into a computer, right? It's just a little for loop where you just loop over, evaluating the function at each of these little grid points. You just need to remember the coefficients in here. But the advantage now is that the error is much better than the trapezoidal rule, or it should be. It's expected to be, right? Because you have this much better bound. So you can get away with using less points, meaning you're looping over less points, right? So you have a much faster program if you're doing this, if you're actually writing down a computer program. So let's go back to our example. let's find an upper bound on ES with our integral we just worked with. So we found an error of 1/12. We're going to use with n equal to 4 again. Well, we know that ES is less than or equal to m b minus a to the 5 over 180 n to the 4, which is m, which we haven't calculated yet, b minus a, that's 2, so 2 to the 5, that's 32. So let me throw this out front. 32 m divided by 180, and then 4 to the power of 4. Now, the question is, what is m? We'll come back to that in a moment, but we need 4 derivatives. So we take f of x is equal to 5x to the 4. You can differentiate this thing 4 times. It's actually going to be a constant function. It's going to be 120. So the absolute value of this thing is also equal to 120. And we can take m equal to 120. 120 is a bound of the constant 120, right? That's a perfectly logical thing to do. So then I get 32 times 120 over 180 divided by 4 to the power of 4, which in this case, coincidentally, comes out to be 1/12, which is exactly the error that we saw, right? So this tells us that using Simpson's rule, with 4 steps, the predicted error, the maximal allowable error here is 1/12, which turns out to be exactly the error that we got. Now, we can turn this question on its head too. Maybe you are sitting at home and you're saying, okay, I want this definite integral computed, the value of it, up to 4 decimal places. Okay, well then how do we do that? Well, let's look at another example. We can use these formulas to guarantee that we have the desired accuracy. So estimate n needed to approximate the same integral. We're going to use the same one, 5x to the 4 dx, with an error within an error of 10 to the minus 4. Okay, so what we know is that our error is less than or equal to, so it's bounded by, again, m b minus a to the 5 divided by 180 n to the 4. And what we're saying is that we want that thing to be smaller than 10 to the minus 4. So if we could find n that satisfies that right there, going backwards in this inequality tells us that the error is smaller than 10 to the minus 4. So let's write this a little better. We knew that m was 120. We knew that b minus a is 2, so 2 to the 5. I have 180 n to the 4, and this is less than 1 over 10 to the power of 4. Now, you can rearrange this and you can find what n to the 4 has to be. So it says n to the 4 has to be greater than 64 times 10 to the 4 divided by 3. And so now we're going to take a 4th root. So taking the 4th root on the 10 to the 4 leaves me with a 10 out front. And now I have 64 divided by 3 to the 4th root, which is approximately 21.5. So n has to be bigger than 21.5. Again, n it has to be an integer, so 21.5 is not going to cut it. And it has to be even. So the first even number first even integer that's bigger than 21.5? That's 22. So we can take n equal to 22 to guarantee e to the s is less than 10 to the minus 4. Okay, so that's pretty cool, right? You could really push this, right? And you could say, okay, a computer, it typically outputs, say my machine outputs 16 digits, okay? And so what I want to do is I want to guarantee that my computed value using the Simpson's rule is exactly what the computer prints out. Well, then what I can do is I can compute the number of steps required in this exact way that we just did this in order to guarantee that my error is smaller than 10 to the minus 16. So that means the first 16 decimal places that I see are exactly the solution. The only difference might be in the digit following that. So you can do this to get like arbitrary precision. Now, of course, this comes with a trade-off, right? The values of n might be ridiculously large depending on what the integral is and how big of an interval you're using. But nonetheless, in theory, we can always find n large enough.